We're back to everyone's favorite analytic method, and that is guessing. Okay, so we're going to start by looking at a specific example of a damped harmonic oscillator. Let's look at d squared y dt squared plus 3 dy dt plus 2 times y equals 0. So this is a specific situation. And if you remember back earlier in chapter 2, I said a lot of times we'll, if we're doing analytic methods, a lot of times we like things as a second order differential equation, and a lot of times systems will be more useful for doing more qualitative or numerical techniques. Again, not true always, but kind of a rule of thumb that we're going to be following a lot of times. So if we're looking for some solutions, we're going to kind of look at this equation and say, okay, is there a type of function that we know about that when you look at its second derivative, you can like add its first derivative and the function itself, and you might get 0. Well, I think your first thought might be sines and cosines. It might be exponential functions. Thinking like, oh yeah, sine, take the second derivative of sine and you get sine again. The first derivative is cosine, but cosine's also some translation of sine, so maybe that'll work if we have sines and cosines. You could also think about exponential functions. We're going to run with exponential functions here and see what we get. Again, there are many ways of finding solutions for this. In chapter 3, we really talk a lot more about finding solutions for equations like this. Specifically, this is a linear equation with constant coefficients, which is a very nice kind of system, but can still lead to some interesting things, as you'll see in chapter 3. So let's just start by kind of guessing. What we're going to guess is say, okay, maybe our solution might look like some constant times e to the st. I don't know what s should be. And we're not going to really worry about the constant right now, okay? Right? We can see here that if this is our thing, we can multiply this by any number and it's still going to be true, right? Because when you take the second derivative or the first derivative or the function itself, right, a constant in front of this can be factored out of all of these, and so it's still going to be a solution. So we could put a c here, but let's not worry about that right now. And you might say, why the heck do we use s? And the answer is s is often used in engineering. So we'll get you some practice working with s's. We also often use lambda in our class as well. In chapter 3, we'll be using both lambda and s. We'll talk a little bit more about why we use those in chapter 3. Again, lots of teasing for the fun stuff that's coming up in chapter 3. So now what I would recommend, you know what I'm going to say, pause the video. If this is your guess, what might s be that makes this true? Pause the video, see if you can figure it out. So if you do that, right, this is going to be your first derivative. This is going to be your second derivative. And when you plug everything in, you're going to get s squared e to the st plus 3s e to the st plus 2 e to the st equals 0. We'll be able to factor out an e to the st out of everything and get s squared plus 3s plus 2 equals 0. If something is factored and equal to 0, that will happen if either piece is equal to 0. We know exponential functions are never equal to 0, right? There's no value of s that will make this ever equal to 0. Also, specifically, we want this to equal to 0 for all time. It seems to be true everywhere. So we're going to just say, okay, well, what value of s will make this equal to 0? And that'll give us an answer. When we solve that, this is a quadratic. We're going to get s plus 1, s plus 2. You could use the quadratic formula. You could complete the square, or you could factor. And again, I'm going through this quickly. This is algebra. And I'm not saying you need to perfectly remember algebra, but you can go review that maybe elsewhere. Okay, so we get 2 values of s that make this true. So we get 2 functions that make this true, specifically e to the negative t. We'll call that y1. And y2 is e to the negative 2t. These are the 2 values of s's that make this true. We have guessed 2 solutions. Again, we haven't talked about initial conditions at all. We're just curious about what solutions might look like. And we found 2 of them. All right, that's great. What do these solutions look like over time? Well, we can plot that. We'll talk more about the phase portrait in the next one. But what this looks like, right, is, well, the position starts at 1 and either decays following e to the negative t, oops, or decays according to e to the negative 2t, right? This is y1. Y2 has the same initial, right? But it decays twice as fast, right? It's a bigger decay constant. So again, labeling our axes, this is the time axis and this is the y-axis. So this is saying for this initial condition, this is one solution, and this solution, and again, we know the initial condition right here. This is for an initial condition of y of 0. Oh, yeah. This is for the initial condition of y of 0 equal to 1. And what initial condition is this for the derivative? -1 and -2, respectively. All right, so these are different situations, which makes sense, right? If we have nice functions, we should have unique answers. All right, so in the first case, this would be your initial condition. And in the second case, this would be your initial condition for velocity. So what this is saying is if you have a spring, right? Let's put this in context, right? If you have a spring that's starting out 1 unit to the right, again, here's going to be y equals 0, 1 unit to the right, and it's starting with a velocity of -1, what happens? Notice the position never goes negative here, according to this solution, right? If we read this over time, this is saying that we have just the right initial position and just the right initial velocity that actually just kind of springs back to equilibrium, springs back to y equals 0 because it's damped in a certain way, the coefficients work in a certain way. This is actually a very special solution. We have no oscillation at all. Very special solution. The other one's also very similar. The green solution behaves very similar to the red solution. In the next video, we're going to talk about what the phase portrait looks like right here. And we're going to see that these two solutions we found are pretty weird, actually, right? When we think of oscillators, we think of oscillating, right? We think of going up and down. These are only going down. In this model, these two solutions we found with these initial conditions are really just approaching the equilibrium and are not doing any oscillation whatsoever. That's a special thing we'll also talk about in chapter 3. Oh my gosh, so many connections to the future. Call me a fortune teller. That's what we've got. Next video, we'll talk about the phase portrait and really see what's going on. Why is this so weird?